Root locus is a plot of all the possible roots of a polynomial where one parameter varies. In this class, we're always going to look at the form of a polynomial that looks like this. D of s plus k times n of s equals 0. Both d of s and n of s are polynomials in S. Let's let OD equal the order of d of s, that is the order of the polynomial, and ON equal order of n of s. In this class, we're going to require that OD is always greater than or equal to ON. And from this, we can state that the order of d of s plus k n of s, the polynomial of interest, will be equal to the order of the d polynomial, since it's the largest polynomial. Now here are some practical tips for drawing the root locus. 1. The root locus will be comprised of a set of points that represent the possible solutions to this polynomial as k is varied from 0 to infinity, and there will be OD branches on the root locus. If you have a second order polynomial, you should expect there always to be 2 roots. Makes sense. If there's a third order polynomial, you should always expect 3 roots or 3 corresponding branches. Number 2. We are going to vary k between 0 and infinity. The root locus starts at k is equal to 0, and the starting point will be where d of s is equal to 0. That's also called the poles. When k is equal to infinity, the root locus will be at the poles of n of s equals to 0. Those are also called the zeros. If the order of d is greater than the order of n, this creates a problem because the root locus always has the same number of branches as the order of d of s, because that's the order of the polynomial. If the order of n of s is less than that, then somehow we're missing branches. And we know that the root locus ends at the zeros, that is the roots of n of s, but we have fewer of those. So if this is the case, then remaining roots are at infinity. The location of those infinities depends on the number of roots at infinity. So let's let nd equals OD minus ON. That is the difference between the order of the d polynomial and the n polynomial. That's the number of zeros that we'll have to have at infinity. And the pattern looks like this. This is nd is equal to 1. We have a 0 at infinity here. Nd is equal to 2. We have zeros at plus or minus infinity in the imaginary axis direction, but we don't know where they're located on the real axis. So we could have plus or minus infinity over here, or plus and minus infinity over here. Nd is equal to 3. We have a 0 here, a 0 here, and a 0 here, where this is 120 degrees. And finally, nd is equal to 4. We have 4 zeros, where these are at 90 degrees. Number 3, the root locus is symmetrical about the real axis. This is because our system is real, and so roots always come in complex conjugate pairs. Complex conjugate pairs are symmetrical about the real axis. Number 4, root locus patterns are similar for similar pole zero patterns. That is, if you have a pattern of poles and zeros, the root locus will take on a certain form. If you have another set of poles and zeros where the pattern is similar but not the same, they may be shifted in different directions or scaled so that they're larger, further away from the axis. The pattern for the root locus is still the same. So once you learn a pattern, it's easy to reapply that pattern. 5. Use brute force to fill in the gaps. The polynomial that we're interested in is d of s plus k n of s equals 0. If you don't know what the root locus looks like, just start picking values of k, plot the corresponding roots to this equation. And number 6, don't worry about all the rules in the text. When root locus was originally devised, we didn't have powerful computers and we couldn't nearly instantaneously compute the roots of higher order polynomials. So there are all sorts of rules that came about that allowed you to approximate what the roots would look like. If you don't know, if you can't use the simple rules and get the pattern of the root locus, just brute force it out. Let's look at some examples. Let's look at this polynomial. It's a linear polynomial, and I want to know what are all the roots of this polynomial if k goes between 0 and infinity. Begin by plotting the poles of the system on the complex plane. The poles are the roots of the polynomial d, that is the part that's not multiplied by k, in this case minus 5. Then plot the zeros. The zeros are the part of the polynomial that is multiplied by k, d, in this case minus 6. The root locus will only have one branch because this is a first order system. The roots will start at the poles and go to the zeros. And that's every possible solution lies in that segment right there. Now you should be able to verify that by just picking values for k and solving the corresponding equation. Here's another example. X plus 5 plus k is equal to 0. Here's the d polynomial. Here's the n polynomial. In this case, it's just 1. Plot the roots. We begin with the poles of the system, that is the roots of the d polynomial, minus 5. Next, we plot the roots of the n polynomial. In this case, the n polynomial has an order lower than the d polynomial, so we must have some zeros at infinity. The order of the d polynomial is 1. The order of the n polynomial is 0. I'm going to slide back up. Look at my location for the zeros. There's 1 0 at infinity out here because the difference between the order of the n and the d polynomial is 1. That means I have a 0 at infinity. The system starts at the poles, goes to the zeros, and the root locus looks like that. Here's another example. We're going to plot this. Here's the d polynomial. Here's the n polynomial. The roots of the d polynomial, you can do the math on this. They are minus 2 and minus 3. Now we need to know whether the roots of the n polynomial doesn't have any roots, and we note that the system is second order, so it should always have 2 branches, and the difference between the d and the n polynomial has an order of 2. That means we must have 2 zeros at infinity, and you can scroll back up in your notes and you'll find that the 2 zeros at infinity will occur somewhere plus and minus infinity, but we don't know where. Now here's where the patterns pay off. I'm going to tell you where. When the pattern looks like this, there are 2 real poles and no real zeros. The zeros at infinity happen right in the center, and so the root locus looks like this. And as k increases, the roots begin at minus 3, minus 2. They come together, and right in the middle at 2.5, they become complex. The real part stays at minus 2.5, and it continues on to plus and minus infinity. Once you know this pattern, it works for every system that has a similar pattern of poles and zeros. Let's look at another example. We want to know what are all the possible roots for this system. Again, we'll plot this. Here's the d polynomial. Here's the n polynomial. The d polynomial has roots of minus 4 and minus 6. The n polynomial has no roots, but we need 2 of them because it's the system's second order, so we need to figure out where are the 2 zeros at infinity. We've seen this pattern before. Scrolling up. Look, 2 poles on the real axis, 2 zeros at infinity. I know that the roots must be here and that they must break or cross right in the middle at minus 5. You should be able to verify this. Pick a number for k. You will find that once they become complex, there will always be minus 5 plus or minus some imaginary value. Let's look at one more. I want to know what are all possible roots to this equation when k is varied from 0 to infinity. Here's the complex plane. This is the d polynomial. This is the n polynomial. The roots of this are minus 4 and minus 6. That's where the root locus starts. It ends at the roots of n of s. Well, it has 1 at 15. I need 2 of them. The order of n of s is 1 less than the order of d of s. Therefore, there must be 1 0 at infinity on the real axis like this. The root locus starts at the poles and goes to the zeros, but I can't have sections that overlap. So I need a pattern that gets me from the poles to the zeros without overlapping, and the pattern looks like this. This pattern is symmetrical about the real axis. It starts at the poles and it ends at the zeros. The exact crossover point here and here I don't know. I would have to do some trial and error to find those. My guess is that this is approximately minus 5. This point I don't know. But once you see this pattern of pole, pole, 0, again, you'll know that the roots go together, break off, meet again on the real axis, and go to the respective zeros. Over time, you'll become familiar with various root locus patterns, and it'll be easy for you to draw an approximation for the root locus, and then pick a couple of points that you need to verify just by picking in a value of k, solving for the roots, and marking them on the graph.